Okay, in this section we're going to be solving systems of linear equations, and we're going to be doing it by graphing. So previously we solved linear equations and it had one variable in it and we just solved for the variable. Now we're going to be having two equations with two variables and we're going to be solving for both of the variables. So two or more linear equations is called a system of linear equations. And the xy values that we find are going to represent an xy coordinate where their graphs intersect. So let's do these first examples here. Let's determine if each ordered pair is a solution to the following system. So this is what a system of linear equations looks like. Just two linear equations with two variables in each of them, x and a y. Okay, so the curly bracket is there just to kind of represent that they're together in one system. So what we have to do for this to determine if each ordered pair is a solution is we have to plug them in. So let's start with the first one, x plus 2y equals 2. So we have to plug in 4 into x, negative 1 into y, and make sure we get a true statement. So we plug in a 4. We plug in the negative 1. That gives us 4 minus 2 on the left. That gives us 2 equals 2, which is correct. So we also have to make sure that we have it for the right-hand side, or for the second equation. So it's x minus 2y equals 6 for the second equation. So we plug in 4, plug in negative 1, and we make sure that it works. And on the left-hand side, we get 4 plus 2. So we do get 6 equals 6, which is true. So that means that this coordinate 4 comma negative 1 is a solution. Okay, let's do another one here. So we have negative 4 comma 3. So we're going to plug it in that first equation, which was x plus 2y equals 2, and see if we get a true statement. So it's going to be negative 4 for x and 3 for y. So that gives us negative 4 plus 6, and that does give us 2 equals 2, so it works for that one. And the second equation was x minus 2y equals 6. So we wanted to see if this was a solution for this one also. So we plug in negative 4 for x, 3 for y. That gives us negative 4 minus 6 equals 10. That gives us negative 10 equals 6, which we know is not true. So that means that negative 4 comma 3 is not a solution. Okay, so graphically speaking here, like I mentioned at the top of the page, the solution for that first one, for A here, 4 comma negative 1, that represents the point where they intersect. So we could graph these, which we'll be doing in a second. If we graphed x plus 2y equals 2, if we solve that for y and get it in y equals mx plus b form, we can graph it. So if we graphed both of these lines, the first one would end up looking something like this. And then the second one would look something like this. So those are both of the equations graphed separately. So right here where they intersect, that is at the coordinate 4 comma negative 1, which we found in part A was the solution. So that's what it represents. The coordinate that we find that's a solution is the point of intersection for the two graphs. Okay, so here are the steps for actually solving them by graphing, which we'll be doing for this section. So step 1 is going to be graph each equation separately. Then we're going to find the coordinates of the point of intersection by observing where it is. And then we have to check to make sure that the ordered pair is a solution by substituting it back in both of the original equations and making sure that it works. So for example, let's solve this by graphing. So let's do that first one. So we have 2x plus 3y equals 4 and 3x minus y equals negative 5. So we're trying to find x and y such that both of these equations are true. So taking a look at the first equation, we're going to solve this for y. Solving this for y, we have to subtract 2x on both sides to get y by itself. So we get 3y equals 4 minus 2x. And then we have to divide both sides by 3. And I'm going to write this in y equals mx plus b form. So I'm going to write it as y equals negative 2/3 x plus 4/3. So that's the equation number 1. So let's solve for the other one, for y. So it's 3x minus y equals negative 5. So I'm going to add y on both sides. And we get 3x equals negative 5 plus y. And then I'm going to add 5 on both sides. And we get y equals 3x plus 5. So here are both of our equations, so let's graph them. So graphing the one on the left, y equals negative 2/3 x plus 4/3. It's a y-intercept of 4/3, which is a little bit more than 1. So it's going to be right here, and then it has a slope of negative 2/3, so down 2 and over 3. Put it about right here, and then we connect them. So we get that, and then the other equation, y equals 3x plus 5. That is a y-intercept of 5, a slope of 3. So that's going to look something like this. And this is y equals 3x plus 5. So looking for their point of intersection, their point of intersection is right here. So that looks like that's the coordinate negative 1, 2. So we're going to check that to make sure that that does work. So we're going to check to see if negative 1, 2 is a solution. So we're going to plug it in both of the equations. So y equals negative 2/3 x plus 4/3. So we're going to plug in 2 for y, negative 1 for x, and we're going to simplify. So on the right hand side, we end up getting positive 2/3 plus 4/3, which is 6/3, which does equal 2. So it works for that one. Then we have to check if it works for the other one. So we're going to check it for y equals 3x plus 5. We're going to plug in a 2 for y, a negative 1 for x. We simplify that right hand side. It's going to be negative 3 plus 5, which does give us a 2. So since it works for both of those, we know that that is our answer. So I'll write it right down here. Negative 1, 2 is the solution. So x equals negative 1 and y equals positive 2. Okay, and then for the next thing before we get into the other types of examples here, there's actually, if you remember when we were solving linear equations, one linear equation with one variable, there's actually 3 types of solutions that we can get. The one that we just did was one example where it had one solution. If we have a solution where we get one answer, it's called a consistent system or an independent equation. The other 2 options that a linear equation can also have no solutions. So if it has no solutions, we call those inconsistent systems. Or it can have infinitely many solutions, and we call those consistent systems. And if they have infinitely many solutions, we say that these equations are dependent. Okay, so let's kind of see what that actually means graphically. So if we have one answer, just like we got in that previous example, we have one answer. That means the lines intersect at one point. So down here, that would be the graph down here on the left where they graph or where they intersect each other. If they have no solution, that means the lines are parallel, so they actually never intersect. So that's going to be the middle graph down here where they're parallel. If they have infinitely many solutions, that means they're actually the same exact line. So you can see down here, infinitely many solutions, they're both lines right on top of each other. They're actually the same exact equation. Okay, and just a reminder here, if two lines are parallel, that means they have the same slope, different y-intercept. If two lines are identical, they have the same slope and the same exact y-intercept, which means they would be the same exact equation. So let's do this example. Let's solve this by graphing. So we have 2x plus y equals 2 and 2x plus y equals 8. So let's solve them both for y, get them in y-intercept form, y equals mx plus b form. So this first one, we have to subtract 2x on both sides. And we get y equals negative 2x plus 2. So that one's actually already done. And then the second one, we have 2x plus y equals 8. And we subtract 2x on both sides. And that gives us y equals negative 2x plus 8. Okay, so graphing these, we have y equals negative 2x plus 2. So negative 2x plus 2 is going to have a y-intercept of 2. Slope of negative 2, so down 2 to the right 1. So that's going to look something like this. And for the other one, y equals negative 2x plus 8. Negative 2x plus 8, y-intercept of 8, slope of negative 2. Connect those ones. That's going to look something like this. So negative 2x plus 8. So these lines clearly don't intersect on this graph, and we know they don't intersect at all because they're actually parallel. So that means parallel when you put two arrows on a line like that. They have the same slope and a different y-intercept, so they're parallel, so that means there are no solutions. They never intersect. Okay, and for the next one, we have 2x plus 5y equals 1 and 6x plus 15y equals 3. So let's graph both of these. So the first one, 2x plus 5y equals 1. Solving this for y, we have to subtract 2x on both sides. So it's 5y equals 1 minus 2x. Divide both sides by 5. And I'm going to give that denominator to both terms in the numerator and just rewrite it so the x term is first. It's negative 2/5 x plus 1/5. And let's solve the other one for y. So 6x plus 15y equals 3. So subtracting 6x on both sides, we end up getting 15y equals negative 6x plus 3. And I'm going to divide both sides by 15 to get y by itself. So giving that 15 denominator to both terms in the numerator, we end up getting negative 6 over 15 for the x coefficient plus 3 over 15. This can actually simplify. This can simplify as negative 2 over 5x plus 1 over 5. So if you notice right now that these are the same exact, they simplified to the same line. They're the same exact equation. The one on the left is the one on the right. So that means there's going to be infinitely many solutions. So let's just graph it real quick. So it's going to be negative 2x plus 1/5. That's a y-intercept of 1/5. And a slope of negative 2 over 5. So down 2 to the right 5. So it looks like this. Y equals negative 2/5 x plus 1/5. So like we said, since it's the same line, there are infinitely many solutions. Okay, so let's do one more here. Oops. So we have negative 3x plus y equals negative 3 and y equals x minus 3. So the first one here, we have negative 3x plus y equals negative 3. So solving this for y, we're going to add 3x to both sides. And we get y equals 3x minus 3. So that one's already done. And the next one, we have y equals x minus 3. So that one's actually already done. That's already solved for y, so we can graph these now. So graphing the first one, y equals 3x minus 3. 3x minus 3, y-intercept of negative 3, slope of 3. So it looks something like this. This is 3x minus 3. And next, for graphing x minus 3, y equals x minus 3. X minus 3, y-intercept of negative 3, slope of 1, so up 1 over 1. So that'll look something like this. So seeing where they intersect, they both had the same y-intercept. So that should have been a hint that they're intersecting right here at that same y-intercept. So that's going to give us an intersection point of 0, negative 3. So we should check, I'll leave it to you guys to check, plug that back in those equations to make sure that it works for both of them, and it will. So that means the coordinate 0, negative 3 is the solution. So x equals 0, y equals negative 3, that will work for both of these equations. Okay, so that is it for this section.